Hello, I'm back again. Okay, now we talk about the various operation modes where we have design, analysis, and prediction. And there's a hierarchy between these modes. You switch them on and off by setting the first parameter to 1 or to 0. 1 is on, 0 is off. And if all of them are 1, as here in this example, design wins. If design is 0 and analysis is 1, then analysis is highest in the hierarchy. So even if design is 0, analysis is 1, and prediction is 1, the code is going to compute with the analysis operation. So what's the difference between them? Well, when I developed the code, I had already some experience in working at the university and also as a consultant for the wind energy industry. And different institutions are interested in different things. So it has happened that that companies have sent me a blade design without any further specifications. That is, what's the blade pitch setting, what's the rotor RPM, what's the range of wind speeds, etc. So if you have a blade design lying in front of you and you don't really know what tip speed ratio, RPM, wind speed it was designed for, the design mode allows you to sweep over a range of tip speed ratios and blade pitch settings. So here in this example, n is the number of tip speed ratios 10 between a minimum tip speed ratio of 2 and 20. Okay, so that's a total of 10 tip speed ratios and a total of 2 blade pitch settings only, with a minimum of 1.8 and the maximum of 3.0. So what it means then in the end is that you get a total of n TSR times n pitch equal 10 times 2, 20 different cases. And this is all in the screen.output that we opened earlier. Okay, you can find this there. If you are in the design mode and these were your specifications, it tells you which tip speed ratios and blade pitch settings the code is going to analyze. In this case, 20 cases at once. If instead you switch to the analysis mode, things work a little differently. So while here you had really power coefficient, thrust coefficient computations as a function of a sweep of tip speed ratio and blade pitch settings, you can plot a 3D curve with that and find for which combination of tip speed ratio and pitch angle you actually get the maximum power coefficient. It's very useful for that. What you do in the analysis mode now is you specify exactly the pairs of tip speed ratio and pitch settings that you want to look at. So here we have tip speed ratio ANA, meaning analysis mode, and pitch ANA, meaning blade pitch settings in analysis mode. And you have 10 cases, specify 10 cases, and then you have an array of 10 numbers, starting from the lowest to the highest. Starting from the lowest to the highest. Even though here in this example you're not changing the pitch settings, you have to specify 10 entries into the array called pitch ANA. Otherwise it won't work. Technically, you can, in the analysis mode, specify 20 cases and then manually fill in the entries so that you would get the same cases as you got for the design mode, but it's much easier to use the design mode for that purpose. And if you do that in the screen.out again, you get now 10 cases, and each case has a number, and it tells you exactly the specifications for the pairs of tip speed ratio and blade pitch angle. Last mode is the prediction mode. I talked about the hierarchy of design versus analysis versus prediction. So the only way to make prediction mode to work is you have to set it equal to 1, but not only that, you have to set the other two, analysis equal to 0 and design equal to 0. The prediction mode is really the practical engineering mode, because here you specify physical blade radius. This is again an example of the phase 6 rotor, 5 meter blade, the air density, the dynamic viscosity of the air, and the number of prediction cases. Here in this case 2, so we're looking at wind speed of 5 meters per second and 7 meters per second. Rotor RPM in prediction mode was 72, and blade pitch settings is constant. So we know that the tip speed ratio is omega r divided by V wind. So omega times the blade radius divided by the wind speed. Omega is nothing but twice pi over 60 times the rotor RPM, then times the blade radius divided by the wind speed, gives you the tip speed ratio. So in screen.out, the physical inputs that we have here in terms of the wind speed in meter per second, the rotor RPM in units 1/minute, and the blade radius in meter over here is then being translated into the equivalent tip speed ratio. And that's just what's noted here on the bottom. XTurb does that for you. So in the end, the computational model anyway uses only tip speed ratio and blade pitch, but the user has some flexibility in giving his or her input the way it best suits the user and the application you're looking at. So, I talked about blade pitch. How is the blade pitch angle defined? Let's recall for one moment the velocity triangle, where the wind is hitting the lower surface of the blade. Wind speed is here, V0, from left to right. However, we have induction because we're taking energy out. So the effective wind speed, axial wind speed at the rotor disc, at the blade element, is V0 times 1 minus A. Then we have the circumferential component, omega r, 1 plus A prime, it's the plus A prime because we're adding the wake rotation here. That gives the resultant velocity vector VREL, and this one has an inclination with the rotor plane, which we call the blade flow angle phi. Given the local twist angle, this then will determine the local angle of attack, because the relative velocity vector here is hitting the lower surface of the blade. So for a wind turbine, pitch angle is defined as the total blade twist at the blade tip. Okay. How is pitch defined? Let's recall. Blade flow angle was the sum of angle of attack and local twist. Alpha is the angle of attack. Beta is the total local twist. So if I take the example here from my input file, we had a twist angle of the N-rail phase 6 rotor blade of negative 1.82 degrees. That's the D-twist in this equation. Now, if in the prediction mode we set, or in all the other modes, the pitch angle to 3 degrees, it means then that the total local twist, pitch equal beta tip, will be 3 degrees for that blade. So if we are at the tip, that means the input here is D twist at the tip, and it will be subtracted such that at the tip the total local twist equals the blade pitch angle. So what the code does, it shifts the input twist distribution by exactly the amount such that this negative 1.82 becomes plus 3 at the tip. In other words, it doesn't just add 3 degrees to all the local twist angles, it actually adds about 4.8 degrees, so that the negative 1.8 degrees turn into positive 3 degrees. This has some advantages. Some codes, they don't have this option, and if you want to change the blade pitch settings, you have to change then every single entry in the blade twist parameter. That's pretty annoying. So XTurb doesn't do that. You have a twist distribution and you may want to change that twist distribution during a design process, and then you have one parameter, the blade pitch angle, that defines the shift of all the local twist entries that you may have. Okay, let's round this up here. So for a wind turbine, positive twist again was nose down. Why was that? If I look at the velocity triangle, positive twist meaning we are pitching the blade into the wind, which meaning we're pitching the lower surface into the wind. In other words, nose down from the point of view of the airfoil. And the pitch setting is defined as the total local twist where at the tip, beta subtip. For those of you who are a little bit familiar with rotorcraft, it's different there. Their positive twist is defined as nose up. Okay, if a pilot puts collective pitch, the blades pitch upwards and generate more thrust. And not only that, that pitch angle is typically defined at the 75% radial station. Whatever it is, positive twist for wind turbine and the rotorcraft, it is nose into the wind. For wind turbine, from the velocity triangle, we have seen that it's nose down, or lower surface into the wind, nose into the wind. For rotorcraft that is in climb or on forward flight, the nose moves up into the wind. So the Schmidt's rule says that's consistent between wind turbines and rotorcraft, and for all rotary ring aerodynamicists, positive twist means nose into the wind. Always. The screen dot out then also tells you what we had just said. So it tells you exactly that. So if for case number 1, For instance, your tip speed ratio 7.6 with a pitch setting of 3 degrees. It tells you here it modifies the blade twist from the input, and this is the case for the NREL phase 6 rotor, where the twist angle from the input at the tip is negative 1.82 degrees, and it tells here, well, it's adding 4.8 degrees such that the tip pitch angle becomes 3 degrees, and it shifts all the other twist angle by that amount. So that means you can change the pitch setting independent of the local twist entries. And I always found that a very useful feature in a design process. And the screen note out also tells you these things here again, that positive pitch means nose down or nose into the wind for the wind turbine. That was different for rotorcraft because there it's nose up. Okay, this concludes our settings in the operation mode, and then in a little while we go ahead with all the solver settings.